Hello everybody, Chapter 3, Lesson Foxtrot, Inverse Trigonometric Functions. Our objectives for today are to define the inverse sine, cosine, and tangent functions, as well as evaluate inverse expressions. Up until this point, we've been dealing with trig functions. We've got 6 of them, and our inputs, also known as our independent variable, have been angles. Alright, so 30 degrees, or pi over 3, or any radian or angle measure in degrees. Okay, and our outputs were ratios. So we could have 1/2, or square root of 3 over 2, or maybe even an undefined value. Okay, what happens when we find the inverse of sine, called either arc sine or another notation, sine inverse. What happens is our input, right, our independent variable, is now a ratio, and our output is an angle. So we've talked before about y equals f of x and g equals f inverse of x, and how their domains, the domain of f becomes the range of f inverse, and the domain of f inverse comes directly from the range of f, right? So that's kind of what we're doing here, and you'll see this in a few moments, but the domain of y, or sine x, becomes the range of sine inverse, and the range of sine becomes the domain of sine inverse, or arc sine. So we're about to work with the idea of the inverse function, which we've gone, boy, that's back to chapter 2, I believe. So let's go ahead and get into it. Okay, so let's go ahead and start with a graph of sine x. So sine x goes from 1 down to -1, and we'll graph, let's go 2 periods. So we'll go out here to -2 pi. Make that pi. We'll go out here to pi, and all the way out to 2 pi. Okay, so if I were to graph sine, it would look kind of like this. Not perfect, but it's pretty good. Looks like an S, where these points would be pi over 2 comma 1. Clearly this would be 0, excuse me, pi 0. This would be 3 pi over 2 -1, and this would be 2 pi 0. Okay, let's go backwards. Oh, not my best sketch, but that's okay, it'll work. This would be -pi over 2 comma -1, pi comma 0, -3 pi over 2 comma +1, and -2 pi comma 0. Okay, so when we dealt with inverses before, what we noted was that in order for an inverse to be a function, the original has to pass the horizontal line test. Well, that's an issue here with sine, right? It will be for cosine as well. That doesn't pass the horizontal line test. Okay, so what we do is we naturally restrict the function, and we're going to restrict as close to 0 as we can. So we're cutting the sine function off right here. What that does is, between the yellow lines, those vertical lines, the function will pass the horizontal line test, which means its inverse will also pass the vertical line test. That makes inverse sine, also known as arc sine, a function. So let's go ahead and plot a few points that would match up based on the inverse function. What we know is that these 3 points, -pi over 2 comma -1, 0, 0, and pi over 2, 1 will all pass, will all have points where its domain and range are flipped. So what that means for our inverse function is that the following 3 points will be on our inverse: -1 comma negative pi over 2, 0, 0 will not change, and 1 comma pi over 2. So let's sketch those points. Let's analyze the graph first and just see what that'll look like. So first of all, negative pi over 2, -1. Well, negative pi over 2 is a little bit more than -1, and I know based on the sketch they look like they're about the same. But -1, okay, -1, negative pi over 2 will be right about here. Okay, let's sketch 0, 0. Clearly that won't change. And pi over 2, or 1 comma pi over 2 will be right about here. Okay, so our sketch of our graph will kind of look like this. Okay, that is going to be the sketch of inverse sine, also known as arc sine of x. Just two different ways to think about it. Okay, so let's talk about the domain and the range of inverse sine and arc sine. Well, its domain will be the same as the range of sine. Okay, so the range of sine goes from -1 to 1. Therefore, the domain of the inverse will be from -1 to 1. This is, of course, the domain of f inverse. Okay, and the range also the same. Okay, its range will go from negative pi over 2 to pi over 2. Okay, so I want you to feel comfortable with the fact that the answers that we're about to come up with when we evaluate, you can kind of see at the bottom of the page here right now that we're going to evaluate some trig function or trigonometric expressions. The domain and range are going to, the range of possible outcomes will be between negative pi over 2 and pi over 2, and the domain will be between -1 and 1. Now I'm going to highlight this side of the circle. This is for y equals arc sine of x, or y equals inverse sine of x. Those two are synonymous. I want you to just be comfortable with the fact that our answers are going to be in quadrants 1 and 4. And the reason why I want to highlight this is because this is the angle negative pi over 2. And if we rotate around, this is the angle positive pi over 2. And when it comes to the sine function, this is I don't really care about the x-coordinate, but this is -1. And for sine, I don't care about 0. This is +1. Therefore, our angle measures are going from negative pi over 2 to pi over 2, which ends up being our range of possible outcomes. And our domain, our inputs from -1 to +1, which are the possible inputs for arc sine or inverse sine of x. So let's go ahead and take a look at a couple of examples. So the way I like to think about this is a word problem. Even though it's not your traditional word problem, what these questions are asking are word problems. And the answer to these questions is an angle measure. All right, so our input is a ratio, and our output is an angle. So our answers for inverse trig functions are angles. When it asks for the arc sine of -1/2, that's saying what angle yields a sine value of -1/2. You're going to fill in the blank as we go along to the other examples, right? So in essence, it's asking you this. sine of what angle equals negative 1/2. Okay, so let's think about that on our unit circle. Well, if the sine is negative, that's got to be in quadrant 4, right? When we consider only quadrants 1 and 4, like I've got in this diagram at the top. Well, if the sine is negative 1/2, okay, that puts me negative 1/2. That makes this square root of 3 over 2. Of course, we're dealing with the unit circle. So this angle right here, theta, would have to be negative 30 degrees. Or we could say negative pi over 6. You can see how your input was a ratio, and now your output or answer is an angle. So in the second example, let's take the negative 1/2 out of play here, and let's use square root of 3 over 2. So my first indicator is that my sine, my angle, or excuse me, my ratio is positive, so that's going to put me in quadrant 1. Again, with inverse sine, you're only in 1 or 4 for your quadrants. So if my sine value is square root of 3 over 2, that would make the cosine value 1/2. Of course, hypotenuse is 1, we're in the unit circle. So this angle theta would have to be 60 degrees, or pi over 3. Okay, awesome. I'm going to go back again, knock out my ratio of square root of 3 over 2, and I'm going to ask, where is the sine, for what angle is the sine equal to 2? And in the unit circle, you'll never ever see a number for sine greater than 1 or less than negative 1. Therefore, theta does not exist. Right? If you look at the unit circle, or at any circle of radius 1, right? If sine was 2 way up here, that can't happen, right? Because the radius here is 1 unit. Therefore, that angle does not exist. There's no solution. All right, let's move on to inverse cosine. Okay, so here we are with cosine. Let's go ahead and graph cosine. We're going to go up to positive 1, down to negative 1. Let's graph. A period on each side of the y-axis. Okay, so cosine looks a little something like this. We're going to put some restrictions on cosine because it will not pass the horizontal line test. Therefore, its inverse will also not pass the horizontal line test, or it will not pass the vertical line test, excuse me. Okay, so naturally, what we would do here, of course, is we would find some restrictions. So clearly, if you did the horizontal line test, it wouldn't pass, right? So what we're going to do is now, like we did with inverse sine, we restricted sine. Now with cosine, we're also going to restrict to 0 to pi. With inverse sine, we restricted negative pi over 2 to pi over 2. But the reason why we restricted is 1, it passes the horizontal line test then, and 2, it's really, really close to 0, so we don't have to find large coterminal angles. So this point here was the point pi negative 1. This point, of course, is pi over 2, 0. Okay, and this point here is 0, 1. Okay, so now we're going to sketch inverse cosine in red. So if the following points are on cosine, what was my third? Pi, comma, negative 1. Then the following points, if they are truly inverses, should be on inverse cosine. 1, 0, and 0 pi over 2, and negative 1 pi. Okay, so let's sketch these. So I should get 1, 0, which would be right about here, and 0 pi over 2, which would be right about here, and negative 1 pi. Ooh, pi is going to be kind of way up here. Okay, there we go. negative 1 pi. Okay, so this graph should take shape kind of like that. Okay, so now let's talk about domain and range of inverse cosine. The domain clearly would go from negative 1 to 1, just like arc sine, right? And that's because we've got max values on cosine of 1 and min values of negative 1. Range would go from 0 up to pi. That's our largest possible output. Now, if we think about the domain, and the domain is related to cosine, therefore, cosine is the x values on the unit circle. If we're going to go from negative 1 to 1, again, I don't care about the y value on this. All I care about are the x values, because those are the cosine inputs. All right, the x values we consider cosine values in the unit circle. The range would go from 0 to pi. All right, so this angle here is 0, and this angle here is pi. Therefore, when we look at outputs, we're going to get outputs, unlike arc sine, we're going to get outputs from 0 to pi in quadrants 1 and 2. So let's look at a couple of examples here. Evaluate the following. So I want the arc cosine of square root of 2 over 2. That's the same as asking me the cosine of what angle theta is equal to the square root of 2 over 2. Right? So if I set this equal to theta, it's going to be an angle. The output will be an angle. So what angle within quadrants 1 and 2, okay, quadrant 1 being here, quadrant 2 being here, would give me the square root of 2 over 2. And clearly, if you're not familiar with this yet, you're going to see some kind of pi over 4 or 45-degree angle, coterminal angle. Since the cosine is positive here, since it's positive root 2 over 2, it's going to land in quadrant 1. And therefore, theta would equal either 45 degrees, or you could call it pi over 4 radians. Okay. Looking at this next example, what angle gives me the inverse cosine of negative 1? That's the same as asking you cosine of theta is equal to negative 1. Where is the cosine equal to negative 1? Well, the only x value in the unit circle where you're going to get a negative 1 is at pi. Therefore, theta will equal pi radians, or you could say 180 degrees. Okay, we're going to move on and look at arctangent. Okay, so next on the list is tangent. Let's go ahead and graph tangent. Pull up a purple marker here. Recall that tangent had vertical asymptotes at x equals negative pi over 2. Way out here at x equals negative 3 pi over 2. I'll go a little bit further here because I want to go around 0. X equals pi over 2. And x equals 3 pi over 2. Now, these vertical asymptotes are not limited to just these values. They exist every pi units starting at pi over 2 in both directions. So here's your graph of tangent. Okay, this is a very general sketch, but the zeros would be midway in between. So this would be 0, 0. This would be the point pi over 4 comma 1. This would be the point negative pi over 4 comma negative 1, etc. Okay, now clearly tangent does not pass the horizontal line test either. So we put natural borders here. I'm going to use green this time. We're going to put a natural or a limiting restriction on tangent so that arctangent now will pass the vertical line test. So in between the green lines, we would have a function that passes the horizontal line test and the vertical line test. Therefore, we can now sketch the inverse by plotting these points in reverse order. So the points negative pi over 4 comma negative 1 and 0, 0 and pi over 4, 1 will become, that will become negative 1, negative pi over 4, 0, 0, no change there, and 1 pi over 4. Okay, so let's try to plot that to the best of our ability. Now, pi over 4 is a little less than 1. Of course, this is not to scale, but I'm going to go ahead and sketch this. This is not going to be to scale at all, you guys, so I'm very sorry about that. But our graph is going to look kind of like this, and it's not perfect, but it's going to have to do. Okay, so that's going to be the graph of arctangent of x. Now, the one thing about this, which is kind of interesting, is if you just sketch that, you might think that that function will head off to infinity. It'll grow increasingly to the right with no limitations, and it'll decrease without limitations to the left. But it actually has horizontal asymptotes. So the vertical asymptotes of tangent of x show up as horizontal asymptotes for arctangent. So I'm going to draw those here in yellow. And then we can talk a little bit about what these limitations will be based on tangent. Okay, so there are these horizontal asymptotes, and they are located at y equals pi over 2 and y equals negative pi over 2. And they are there in those locations because the domain of tangent, of course, had restrictions at x equals negative pi over 2 and x equals pi over 2. So now the inverse has restrictions at y equals negative pi over 2 and y equals pi over 2. Okay, so the domain and range of arctangent. The domain of arctangent is like the range of tangent. There's no restriction. So we could say all real numbers, or you could say from negative infinity to positive infinity. I can plug any number into tangent with no restrictions. Okay, but the range is going to be restricted. The range will not include negative pi over 2 and pi over 2, but it will be possibly everything in between. It can take on any input or output within negative pi over 2 and pi over 2. So our natural restriction on arctangent are answers that land in quadrants 1 and 4, very similar to arcsine of x. So let's go ahead and look at a couple of examples. Okay, arctangent of 0. Where in the unit circle is the tangent 0? Well, there's two places. So if I'm asking this, theta equals arctangent is 0. That's the same as saying the tangent of theta equals 0. And that happens at two places, right? That happens at 0 degrees, and it also happens at 180 degrees. Okay, that's because we take the y value over the x value, and 0 over negative 1 and 0 over 1 are both 0. But because of the restriction that we place on quadrants 1 and 3, or excuse me, 1 and 4, then theta has to equal 0 degrees, or 0 pi radians. Okay, now let's look at the next example. Where is the inverse tangent? For what angle is inverse tangent equal to negative 1? Again, if you'd like to visualize it this way, where is the tangent negative 1? Now, tangent is negative 1 at some multiple of pi over 4. That should start getting you thinking pi over 4. Now, the tangent is positive in quadrant 1, and it's negative in quadrant 4. So we are dealing with quadrant 4. So as we look at quadrant 4, the only way tangent can be negative 1 is if I have two legs on a triangle giving me an angle that would be what measure? Well, if I did Pythagorean theorem, I would get square root of 2 there, which tells me that theta would be negative 45 degrees, or negative pi over 4 radians. I'll give you one more here. Arctangent of negative 1 over root 3. Negative 1 over root 3. Okay, so tangent, you can see the ratio is negative. That puts us in quadrant 4. A couple ways you can do this. You can either write negative 1 over root 3, right, which would put us in a non-unit circle situation. You'd have to do Pythagorean theorem. You'd see that this was 2, blah, blah, blah. Or you can put that here, negative 1 over root 3, which makes the hypotenuse 1, which then allows you to do Pythagorean theorem there. I prefer the other method. So I'm going to put a negative 1 and a root 3 and a 2, which I know, and I just from experience know that this angle would be 30 degrees, negative 30 degrees, or negative pi over 6 radians. Okay, there you have it. That is arctangent. You're going to get a chance to do a number of evaluating problems of these inverse trig expressions, but I do have one more slide for you that I'd like to go through. Okay, so I'm given a right triangle here with an angle that's unknown, a side that's unknown, and one side or leg that is known. So let's use the Pythagorean theorem to find the missing side or leg. So in the first one, we would take 8 squared plus x squared, and that would equal our hypotenuse, c squared. Okay, so that would be 64 plus x squared equals c squared. Therefore, c would equal the square root of 64 plus x squared. Okay, so this would be square root 64 plus x squared. Okay, so the question is asking us, in each triangle, find theta in terms of x for all 3 inverse trigonometric functions. So what that's asking you to do is to write, first of all, the sine of theta is equal to x over the square root of 64 plus x squared. Now we want to write a function for theta in terms of x. So we want to isolate theta. What that means is that I'm going to use the following. To undo a sine function, I'm going to take the arc sine or inverse sine of the other side. That isolates theta in terms of x for an inverse trigonometric function. Now I could do something very similar. That's using arc sine. Using arc cosine, I would have 8, right, adjacent over hypotenuse. And arctan, I'm going to use inverse tangent just to mix it up, I'm getting wild here, x over 8. So theta would be equal to any one of those. Those would all yield the exact same angle for the same value of x. So it doesn't matter what x is, the angle would be the same using any one of those 3 ratios. Okay, so let's do number 2. Let's use Pythagorean theorem. So 4 squared plus, I'm going to call this, no, I won't call it y, that's a bad decision. How about m plus m squared is equal to x squared. Okay, so let's solve for m. That would be m squared would be equal to x squared minus 16. So m would be equal to the square root of x squared minus 16. Now basically getting rid of this m, this variable, it's just a placeholder, right? So that we can get this in terms of x. So the sine of theta would be equal to the square root of x squared minus 16 over x. Therefore, theta would be equal to the inverse sine of the square root of x squared minus 16 over x. All that this is opposites over hypotenuse. Right? It's just a ratio. That's an input into an inverse function, which will give us an output of an angle. Okay, so I'm not going to do the arc cosine or find theta in terms of arc cosine or inverse tangent. I don't care. That's something you can do on the side. If you have questions about it, please let me know. Let's get to example 3 here and keep moving. Okay, so Pythagorean theorem, I'm going to call this m as well. M squared plus x plus 2 squared is equal to 25. So m squared would be equal to, I don't know how I want to do this. Do I want to expand that? I don't know. Gosh, okay, fine. I'll expand it. That's x squared plus 4x plus 4. So m squared would be equal to 25 minus, nah, you know what? I'm going back on my word here. I'm just going to leave it like this. So m would be equal to the square root of 25 minus the quantity x plus 2 squared. Therefore, I'm going to flip a 3-sided coin. We're going tangent. So the tangent of theta, right, is opposite, which is x plus 2 over adjacent, which will be square root 25 minus x plus 2 quantity squared. So theta will be equal to the arctangent of that thing, that ratio. Okay, and just reiterate, it does not matter whether I use arctangent or inverse tangent in this case. All right, guys, that is it for Chapter 3, Lesson Foxtrot. I will have a part 2 coming soon where you'll do a little bit more with what we've done on this last slide. Hope it made sense. Have a great day. We'll see you in the next video.